In this video, we're going to talk about an introduction to the molecular orbital model as covered in Chapter 9.2 in Zumdahl. So, up until now, we have dealt with molecules that undergo covalent bonding using what's sometimes called the localized electron model. And the problems with the localized electron model are basically twofold. Number one, it doesn't explain molecules or ions that have delocalized electrons. Therefore, we have to add in resonance as a patch to the model. Second, it doesn't work well with molecules or ions that have an odd number of valence electrons, which do exist, but we've pretty much just ignored them up until now. So, scientists replaced this with what is called the molecular orbital model. A molecular orbital is a wave function, but it's made by combining atomic orbitals. And therefore, the molecular orbital spans the entire molecule, not just one atom in the molecule. Like an atomic orbital, a molecular orbital can hold up to 2 electrons, as long as they have opposite spins, according to the Pauli exclusion principle. And, like an atomic orbital, it gives the probability of finding the electron in a certain location. Now, one of the great strengths of the molecular orbital model, which I'll discuss in more detail, is that it can explain the relative bond lengths and bond energies in related species. So let's look into this. We'll begin by considering the simplest molecule that exists, which is the hydrogen molecule, H2. Each hydrogen atom has one 1s orbital with one electron in it. And if we're going to combine the 1s orbitals in a linear fashion, we can do so in 2 ways. We can obtain one molecular orbital by adding together the 1s orbitals on atoms A and B. So molecular orbital 1 is 1sa plus 1sb. Or we can also form another molecular orbital 2, by subtracting 1sa minus 1sb. The first molecular orbital is formed by adding the atomic orbitals, and in doing so, we increase the electron density between the 2 nuclei. And in doing so, that favors bonding, and we're going to call that bonding molecular orbital sigma 1s1. But the molecular orbital formed by subtracting atomic orbitals decreases electron density between the nuclei, and that disfavors bonding, and that's called an antibonding molecular orbital, which we will call sigma star 1s. The star indicates that it's an antibonding molecular orbital, and the 1s indicates that it's coming from 1s orbitals. So let's see what that looks like graphically. In this diagram, we show combining the 2 1s atomic orbitals on the hydrogen atoms in a positive way. That results in constructive interference between the 2 nuclei, and therefore there is a greater probability of finding the electrons between the 2 nuclei. That molecular orbital is called the sigma 1s bonding molecular orbital. But in the other combination, we are adding the 2 1s atomic orbitals out of phase, which is basically the same as subtracting one 1s atomic orbital from the other. That results in what is called destructive interference between the wave functions. And as a result, we obtain the sigma star 1s antibonding molecular orbital. And as you can see, the out-of-phase combination of the atomic orbitals results in a node between the 2 nuclei. That disfavors bonding. Okay. Now, we can represent that with an energy level diagram, and this is what it looks like. On the outside, we have the 1s atomic orbitals of the separate uncombined hydrogen atoms, each of which contains a single electron. When we combine the 2 1s orbitals in a positive and negative way, we come up with the 2 molecular orbitals, the sigma 1s bonding molecular orbital and the sigma 1s star antibonding molecular orbital. And they are shown in between the 2 hydrogen atomic orbitals. And we also see diagrams that represent the electron density. And as we said before, in the sigma 1s bonding molecular orbital, there is a buildup of electron density between the 2 nuclei. But in the sigma star 1s antibonding molecular orbital, there is a deficiency, there is actually a node between the 2 nuclei where electron density cannot exist. Now, as you can see, we place the 2 electrons that came from the 1s atomic orbitals into the sigma 1s bonding molecular orbital, which is lower in energy. And we can then write an electron configuration, a molecular orbital electron configuration for the dihydrogen molecule, sigma 1s 2. Now, let's summarize some important points of this model. First of all, both of these molecular orbitals are called sigma because, as we said before, a sigma orbital is cylindrically symmetrical about the bond axis. In the bonding molecular orbital, there is the greatest electron density between the nuclei. That favors bonding and strengthens the bond. Whereas in the anti-bonding molecular orbital, the sigma star 1s, the greatest amount of electron density is outside the nuclei. The bonding molecular orbital is lower in energy than the starting atomic orbitals, and therefore when we populate bonding molecular orbitals with electrons, that contributes to bonding, meaning it strengthens the bond. However, the anti-bonding molecular orbital is higher in energy than the starting atomic orbitals, and when we populate an anti-bonding molecular orbital with electrons, that detracts from bonding or weakens the bond. And as you saw, each molecular orbital can hold up to 2 electrons as long as they have opposite values of the spin quantum number, consistent with the Pauli exclusion principle, works for molecules as well as atoms. And one cool thing about the molecular orbital model is that we observe what's called orbital conservation. So the number of molecular orbitals you get out by linear combinations of atomic orbitals is always equal to the number of atomic orbitals you started with. Now, this leads to the possibility of calculating something that's called bond order. Bond order is an approximate measure of the relative bond energy, and in general, the higher the calculated bond order, the stronger the bond. And one of the cool things about the molecular orbital model is that the bond order that you calculate for a given species very often corresponds directly to the number of bonds that you would draw in the Lewis structure. So there is some correlation between the molecular orbital model and the localized electron model. So here is how you calculate the bond order. It is equal to the total number of electrons that are placed in bonding molecular orbitals minus the total number of electrons that are placed in antibonding molecular orbitals divided by 2. So we can do this for the dihydrogen molecule. So for H2, we said that the electron configuration is sigma 1s with 2 electrons in it. So therefore, the bond order is equal to 2 electrons in the sigma bonding molecular orbital minus 0 electrons in the sigma star antibonding molecular orbital divided by 2 gives us a bond order of 1. And doesn't that correlate nicely with the single bond between the 2 hydrogen atoms in the H2 molecule? It sure does. Now, this leads us to a concept called magnetism. It turns out that many substances respond differently when you place it near a magnetic field. And a substance is described as paramagnetic if it is strongly attracted to a magnetic field. This is associated with unpaired electrons. Correspondingly, a substance is described as diamagnetic if it is weakly repelled by a magnetic field, and that is associated with paired electrons. So we can use the molecular orbital energy level diagram to predict whether a substance is going to be paramagnetic or diamagnetic based on whether or not it has unpaired electrons. And you can easily see that from the molecular orbital energy level diagram. Now, let's do some applications. For each of the following species, we are going to show the molecular orbital energy level diagram. We will write the molecular orbital electron configuration. We will calculate the bond order, and we will state whether it is diamagnetic or paramagnetic. And we're going to start with some pretty simple species that basically have only sigma 1s and sigma 1s star molecular orbitals. So we already did the dihydrogen molecule, and we can consider the dihydrogen cation, the dihydrogen anion, the dihydrogen dianion, and corresponding species made by combining helium atoms. So let's begin. With H2 plus, we have only 1 electron, so we will place that in the sigma 1s bonding molecular orbital. We'll write the electron configuration as sigma 1s 1. That gives us a bond order of 1/2, and we would predict that that would be paramagnetic because it has an unpaired electron. The dihydrogen anion would have 3 electrons total. Therefore, its energy level diagram would look like this. We would write the molecular orbital energy level, the electron configuration as sigma 1s 2, sigma star 1s 1. That's a 2, by the way. And for this, the bond order would also be equal to 1/2 because we would subtract the 1 antibonding electron from the 2 bonding electrons and divide by 2, giving us a bond order of 1/2. That also has unpaired electrons, so we would say that that is also paramagnetic. Now, for the hypothetical dihydrogen dianion, H2 that would have a total of 4 electrons. We would place 2 electrons in the sigma 1s and 2 electrons in the sigma star 1s. Well, now, populating the antibonding molecular orbital weakens bonding. That gives us an electron configuration of sigma 1s2, sigma star 1s2. That results in a bond order of 0, and that explains why this species does not exist. I'm not going to predict whether it's paramagnetic or diamagnetic because it doesn't exist. Now, let's do the same thing for the helium species. And for the dihelium dication, that would have a total of 2 electrons. Its molecular orbital energy level diagram would be sigma 1s2. That would have a bond order of 1. I forgot to put the electrons in. There they go. And because now we have only paired electrons, we would predict that that would be diamagnetic. For the dihelium monocation, that would contain 3 electrons total. We'll place 2 in the sigma 1s bonding molecular orbital and 2 in the sigma star 1s antibonding molecular orbital. We'll write the molecular orbital electron configuration as sigma 1s2, sigma star 1s1. That would give us a bond order of 1/2, and we would predict that that would be paramagnetic. And then finally, for the dihelium neutral molecule, that would theoretically have 4 electrons. I'll place 2 in the sigma 1s bonding molecular orbital, 2 in the sigma 1 star 1s antibonding molecular orbital. That would give us the electron configuration sigma 1s2, sigma star 1s2. That would be a bond order of 0. And again, we won't say whether it's paramagnetic or diamagnetic. Now, that explains to us in terms of molecular orbital theory why the dihelium molecule does not exist. It would have equal number of electrons in antibonding and bonding molecular orbitals, therefore they would cancel each other out and no bonding would occur. Now, for the other species that have bond orders that are greater than 0, to say that it has a bond order greater than 0 doesn't necessarily mean that we can make the molecule and put it in a bottle. It just means that theoretically it should exist, and most of these have been observed at one point or another. Now, in the next video, we're going to talk about a slightly more complicated species in which we actually start to involve p orbitals. See you then.